What forms can life take? We have not yet discovered alien life, let alone seen what it looks like, but we can imagine. How strange might such life appear to us? Perhaps as strange as the Cabrali amoeba, a single-celled creature discovered in 2009. These may look like aliens, but they live right here on Earth. These microscopic creatures have evolved armored plates and protective pigments, which help to shield them from high levels of ultraviolet radiation and concentrated salt. Because they live in a small body of water on top of a volcano. They inhabit a high-altitude lake in the deserts of northern Chile, a life-friendly microclimate in one of the driest places on Earth. Conditions here might resemble the planet Mars a long time ago. That's one reason why scientists come to Chile, to simulate a trip to the Red Planet. They test rovers here in the Atacama Desert to understand what life, if any, could look like, and how to find it, either as fossils or as living microbes. Life here might hide inside rocks, sheltered from harsh radiation. Could these nanoclimates teach us about the last refuges of life on Mars? Microbe-sized environments where life survives despite difficult conditions around it? Life thrives on Earth. The pale hues of the desert, the blue of the ocean, and the green of the rainforest. These are the colors of a planet that harbors life. Scientists describe these colors with great precision. If we tease apart the colors, the wavelengths of light, we reveal a spectral fingerprint unique to the chemistry of what we're observing. The trees of the forest reflect more green light. The ocean spectrum peaks in blue wavelengths. And the desert's highly reflective surface shows almost no signs of trees or water. All these differences become even more noticeable when we examine light that human eyes cannot perceive. Earth is a living world. Life and our planet evolved together, our destinies entwined. Earth's forests help stabilize our climate. Their trees store carbon and exhale oxygen, and they circulate water too. Below us, we can trace the Amazon River as it travels to the Atlantic Ocean. But the trees of the Amazon rainforest also pump water into the atmosphere, even more water than flows through the river. Winds carry forest water and oxygen to far-flung parts of the globe. We can observe these fingerprints of life in our atmosphere. Sunlight has its own distinctive spectrum. In Earth's atmosphere, oxygen, water, methane, carbon dioxide, and other gases absorb some of that light. This spectral fingerprint reveals that Earth is a living world. We can also detect signs of human changes, industrial chemicals, and an excess of carbon dioxide. These are recent developments, signs of our technological civilizations, like our city lights, which have only shined brightly for a few hundred years. But Earth's surface and atmosphere have been shaped by life for billions of years. Imagine traveling back in time. Before humans, before birds and flowers, before even dinosaurs. More than 300 million years ago, Earth looked very different, and the first great forests were taking root on land. These plants changed the surface of our planet. They broke up rock to create soil, and they buried carbon dioxide from the atmosphere, causing our planet to cool down. Fueled by the light of the sun, plants provided an abundant energy source for animals, including giant relatives of dragonflies more than 10 times larger than the ones we see today. Plants also released oxygen, an important part of life's spectral fingerprint. But when oxygen first appeared on our planet more than 2 billion years ago, it may have caused our planet to plunge into a deep freeze, an icy snowball Earth. Where did this oxygen come from? Life. Long before animals or plants, all life on Earth was microscopic. Some of these microbes evolved a form of photosynthesis, harnessing the power of sunlight and releasing oxygen in the process. Oxygen destroyed greenhouse gases that kept Earth warm, causing the global temperature to drop. This microscopic life changed our world when Earth was just half its current age. But life had existed here for a long time. Previous generations of microbes had modified our planet's chemistry and transformed its appearance. We would have to leap back in time about 4 billion years, shortly after our planet formed, to find it unaltered by life, unrecognizable, and un-Earth-like. Just as life was getting started on Earth, another planet began losing its capacity to support abundant life. Billions of years ago, Mars harbored water on its surface, and water circulated in its atmosphere. Mars was home to frigid lakes, perhaps even an ocean. Under the Martian surface, water likely flowed from the southern highlands to the low-lying northern hemisphere. And where we find water, we can hope to find life. Mars eventually lost its thick atmosphere, and it couldn't support liquid water on its surface. But even though Mars today appears barren, dry, and cold, we can see signs of where water once flowed. And water could still hide underground. Could life beneath the Martian surface have survived as conditions above grew less friendly to life? In these sunken canyons called nili fossi, we have detected invisible plumes of methane. A partial fingerprint of life? Or perhaps a result of chemical interactions between water and rock, like the clay minerals we find here. We also see evidence of hydrothermal activity that could have once provided energy for life. These tantalizing observations make this a promising place to explore further. Perhaps a future mission will visit this area. A single spacecraft could carry multiple probes, releasing them one by one. Each small probe could travel to a different landing site. A successful mission might even find evidence of an appealing nanoclimate, a tiny habitable niche teeming with life. Could Mars still harbor life, even if most of the planet is barren and dead? Both Mars and Earth lie close to the Sun, beneficiaries of its abundant light and energy. We can also search for life farther out in our solar system. All life requires energy, if not from the Sun, then from something like the hydrothermal activity on Mars. We can seek out other sources of energy, from chemistry or gravity. Let's visit one of Saturn's moons, Enceladus. Saturn's gravitational pull squeezes and warms the moon's interior. Geysers erupt from around its south pole, hinting at what lies beneath the icy crust. We have found evidence for an ocean that spans the entire moon. Scientists suspect that the ocean floor harbors thermal vents, releasing heat generated by Saturn's gravity. On Earth, similar vents are home to living communities that don't depend on light from the sun. Could life have evolved on Enceladus too? We don't have any evidence for that, just the hint of similarities to an ecosystem on Earth. But we can search for evidence. The material flowing upward from these vents escapes through cracks near the South Pole. Eventually, this material makes its way to space. A future spacecraft specifically designed to snake down the narrow gap could test the waters for signs of life. Microscopic organisms would change the chemistry of the water, or perhaps survive long enough to be detected directly by the spacecraft. If life exists on Enceladus, it is certainly different from life on Earth. We have to dig deep for signs of life here because this tiny moon hasn't been transformed by life like our home planet. From here, Earth appears as a small speck, a pale blue dot in the starry sky. We can observe it as we observed the rainforest, ocean, and desert. We can tease apart different wavelengths of light to identify the fingerprints of life, measurable even from far away. If we watch Earth for a day, we can see the effects of its rotation. If we watched for a year, we would observe the rhythms of the seasons. If we look at Mars instead, we see no signs of the chemistry or rhythm of life. An apparently dead world. Spectra also reveal what's happening around distant planets orbiting stars other than our sun. We have found thousands of these exoplanets, although some parts of the sky have been more thoroughly explored than others. Can we find worlds that have been shaped by life as Earth has? A planet's spectral fingerprint can reveal the chemistry of its atmosphere, even from many light years away. Let's visit a rather un-Earth-like world to see how that works. Astronomers have observed this star for decades. In our telescopes, we can block the bright light of the star and see the faint light reflected from planets in orbit around it. We can tease out spectra from these points of light and imagine what the planets look like. HR 8799b shows fingerprints of water and carbon monoxide in its spectrum, as well as evidence for thick clouds. But this planet is larger than Jupiter, the largest planet in our solar system, and it revolves far from its parent star, taking more than 450 years to complete one orbit. It is almost certainly a giant, lifeless world. As we find more and more planets around other stars, astronomers are learning to characterize them. Some planets pass between their parent stars and Earth, so we can observe how their atmospheres absorb light. We see signs of carbon dioxide in the atmosphere of HD 189733b. We also know it's a deep blue color, a little like Earth. But it's bigger than Jupiter, with an atmosphere hot enough to melt aluminum, and it orbits so close to its parent star that it zips around every 53 hours. This hot Jupiter is also not a good place to look for life. We have learned about these planets and others by studying their faint spectra. Over the next decade, astronomers will refine these techniques on other, perhaps even weirder worlds. Then, when we look at planets more like Earth, we'll be better prepared to interpret our data. Imagine if alien astronomers could exist on this planet. With the right technology, they might look at Earth and detect signs of life. Perhaps they could tease apart wavelengths of light to identify the spectral fingerprints of Earth's living systems. Or they could observe Earth using radio, a less energetic form of light. In radio wavelengths, Earth would shine brightly thanks to human technology. But not today's technology. Because the planet lies more than 64 light years from Earth, our hypothetical alien astronomers would see our planet as it looked more than 6 decades ago. They would see Earth just as television became more common. As we began using radar around the globe. And as the last few above-ground nuclear tests were taking place. These phenomena create radio emissions that are part of Earth's technosignature, a dead giveaway that a technological civilization existed on our planet. And if this star were much farther away, it could detect nothing. Earth's radio signals would not yet have had time to reach it. Humanity has searched for alien technosignatures for many decades. We have not discovered any, but we keep looking. And we've just started our search for the fingerprints of life on distant exoplanets. Let's return to our solar system to take a look at future technology that could help us spot a faint, distant planet around its much brighter parent star. The challenge lies in blocking out the bright light of the star to see the faint light from its planet. One idea is to devote an entire spacecraft to casting a shadow. This so-called star shade has a unique shape that emerges as it unfurls. Its flower-like silhouette minimizes interference from starlight, allowing astronomers to see very close to a star. An Earth-sized planet in orbit will appear as a small, dim point, reflecting light from the star. We can then tease apart the wavelengths of light to view the planet's spectrum and search for fingerprints of life. We can look for changes over time, like the daily and yearly changes that take place in Earth's atmosphere. And each planet's fingerprint will be unique, with its own features that could hint at the presence of life. To feel confident that we are not alone will require many observations, more detailed data on promising planets, or possible detections of life on a variety of worlds. Right now, we only know one example of life in the universe: us. Over billions of years, life has evolved to thrive on Earth. But our civilization is still young. Our planet's spectral fingerprint looks out of balance, showing signs of unnatural pollutants, of escalating carbon dioxide threatening to warm our planet dangerously. Over time, we can change this. We can learn the lessons of our living world, partnering with life, becoming integral to and interwoven with the natural world. Imagine a future in which our technologies enrich our planet instead of draining its resources. In which humans see themselves as part of nature rather than above it. In which our species forms a vital strand in a vibrant web of life. Such a world could broadcast its presence to the universe for a very long time. Perhaps one day, we will detect the techno-signature of a distant civilization. Eventually, we might find more. Such civilizations can't last forever. Some might burn out quickly, becoming invisible after a period of years, decades, or centuries. Others could endure for thousands of years or longer. The longer a civilization broadcasts, the more likely we are to find it. In fact, if we detect a signal from an extraterrestrial intelligence, it will be a hopeful sign that life out there has survived challenges like those we're facing. How can humanity ensure that we are making our presence known 1,000 years from now? Or 100,000? If our civilization regenerates and strengthens life on Earth, our future can be bright. And our living world might contribute its voice to a chorus of civilizations that span the cosmos.